it's not the area and the curve, what it represents to. Okay, and the second one should be pretty easy. What is the role of the goat anti-rabbit IgG quadratic peroxidase conjugated experiment? So it's asking about ELISA, and the anti-rabbit is a secondary antibody. So remember, it's not the specific one, it's the one that's specific only to the species. So it's the second antibody in the indirect ELISA. Okay? Any questions or confusion about this? Okay. So the third one should be also quite intuitive if you understand how ELISA works. So this is the order that we should follow to do the ELISA experiment. Okay? I think that should be no problem. And then it asks about the SPR graphs. So those are all examples of certain SPR experiment data. So each graph actually gives you different compounds, so they show different profile. It asks which one can be used for equilibrium analysis. So from this question, you should understand it's asking which one can be used for equilibrium. So to do that, we at least need to reach the equilibrium state, right? The equilibrium state includes two types of equilibrium. One is when you flow your samples in, it will first bound, right? That is the association step. So then it will reach equilibrium by binding to all the receptors. So that's the association equilibrium. And in the second step of SPR, we also look at dissociation. So we wash it away using many, like a large volume of buffer. So that will gradually deassociate. And that dissociation process also needs to reach an equilibrium to give you a deassociation kinetics. So basically, we need to capture the full procedure of both processes. Association, like it binds and then reach equilibrium, and also deassociation. So basically, you wash it away, it deassociates and then reaches zero. So basically, you need to pick a graph that reaches equilibrium at both of these steps. So and that's the only C. For A, we can see that it hasn't reached the dissociation equilibrium. So you need to give it longer time here. All right. And same for B. And for D, this step is okay. It's already like kind of flat, but for some of the curves, you can see here the association step, like the binding step, hasn't reached flat. Okay, so like this one, it's not flat yet. So we for this example, some of the compounds hasn't reached equilibrium for binding. So that's why we eliminate D as well. Okay, so only C for every one of them, it's a complete binding and unbinding curve. Okay, any questions here? Okay, cool. And this is also about the SPR experiment, and it asks you more quantitatively. It plots the deassociation rate, the KD, and the association rate, the Ka, on two axes. And it has four different compounds, A, B, C, D. But we, from the lecture, we know that if they fall into a straight line, we know that it should be, it should have the same capital KD. Basically, it should have the same binding affinity, because we know that the big KD is a ratio between the small KD over small Ka, all right? And because the lie on the same line, like the ratio of them are actually the same. So this question asks, what is true? Which statement of the following is true about their KD value? So notice that this is the big KD we are asking about. Basically, the binding affinity, which is the ratio small kd over k. So so this is here. This position on the y-axis is 10 to the power of 6. Basically, it's the small ka of compound B, and we know the small kd of compound B, which is 10 to the power of -3. So we know that the capital KD should be this number over this number, and that is 10 to the -9. So we know that the binding affinity should be 10 to the -9 molar. Okay, and we know that it should be the same. So actually, all the others also has the big capital KD of this number. Okay, so that's why the statement C is correct. Okay, any questions on this one? Okay, cool. Next one, okay, we want a drug that can be effective for longer time. Which one of the above? So it's asking, choosing between this four is a better candidate in terms of this requirement. So basically, it's asking us we want a drug that can last longer. So this statement basically can translate into a requirement that it should have a slower deassociation rate. Basically, the small kd value should be preferably small. So that's why we should pick A, which has the slowest dissociation rate among all four here. All right. So even though they have the same binding affinity, their strength of binding to the receptor is the same. They still differ in other properties. For example, like the duration time. All right. So if we really want one that can last longer, we will go for A. Okay. So that's how we determine that. Okay. So the next question is comparing the log P value of two similar compounds. So they are both, backbone is a benzene ring with 3 hydroxy group, but the hydroxy groups position are different, so that they cause a different log P value. The first one is 0.25, and the second one is 0.35. So basically, the first one is more water soluble. So it asks why the latter, this one, is more lipophilic. Basically, why this one has a smaller water solubility. And the hint is hydrogen bond formation. So I want you to draw how hydrogen bond formation gives you these results. So basically, it's because the intramolecular hydrogen bond formation. For this one, if we draw out the structure of this hydrogen atom, it will be like this. Okay, so you can see this hydrogen would be close to this oxygen, and this one will be close to this oxygen. So they can form like quite strong intramolecular hydrogen bond, so that the leftover hydrogen that can bond with the water molecule is actually much less. For example, these are water molecules like floating around, and because they have many intramolecular hydrogen bonding already, they have less availability to bond with the environmental water molecules. But for this one, if you draw like this, if you draw it by itself, you see that this hydrogen and oxygen will be too far away, so they cannot form intermolecular hydrogen bonding. So all of them will be bonding to the environmental water molecules. So basically, cause them to have a stronger hydration to the solvent. So that's why this one has a higher water solubility than this one. All right. Okay. So that is that. And next question is asking you, there's a drug that has a pKa of 3.5, and it's quite effective in the in vitro tests, basically outside cells. So when we do it in test tube, it's pretty good. It can bind the purified receptor protein, no problem. But the in vivo test actually it showed a poor activity when it's already taken, but good activity when it's injected. So it asks why. I think that's also quite simple to think about, because if you compare the in vivo and in vitro and compare the hourly administration versus intravenous injection, the differences would be whether or not it needs to cross the cellular membrane. All right. So, and we know that pKa is 3.5, and our physiology pH in the human body is about 7. So in that pH, this molecule would be negatively charged. All right. So basically, that means it's highly charged, so that it will make it very hard to cross the cellular membrane, because cellular membrane is very hydrophobic. It doesn't interact well with the ionic charges. So if you take it orally, it needs to go across your cellular membrane to go into your system to be effective. So that's why when it's taken orally, it will have very little of them actually goes into your body. So that's why it's not that active anymore. Okay, so that's exactly the bioavailability we are talking about in the lecture. Okay, so the next question is ask you to do some SER rationale for this molecule. So the answer are not fixed. So as long as you give a reasonable example, that's fine. So I just listed several examples I think about when I look at this question. So as long as your, for example, if you add a methyl group here, if the KD increases, that means you have a worse drug, right? So that may be due to the steric effects of the added methyl group. It affects the binding to the receptor. So your structure should match your reasoning or your rationale to the how the KD changes. As long as it matches with each other and you brings up a reasonable structure activity relationship, you should be able to get the bond. Okay, so you can look at my example here and see how I rationalize it. Okay. So the next question is about IC50 measurement. So it gives you 2 experiments about compound X and Y. And it also gives you this Chomsky equation to ask you to compare which one is a better inhibitor. So that's quite easy to calculate. You just rearrange this equation, and what you need to get is the Ki. So the Ki, you plug in the IC50 from the experiment value, and you plug in the ligand concentration, and this is the Kd value of the ligand, which we already know, this one. So once you plug every number into it, you will calculate the Ki of the respective compound. So when you think about which one is a better inhibitor, you couldn't just look at the IC50, because as we have learned in class, the IC50 will strongly depend on how you do the experiment, how much ligand you put in the experiment. So you cannot be directly compared. When you calculate the Ki, these numbers can be directly compared, and a smaller Ki will represent a more potent drug. So, and now we calculate the Ki of X is smaller than the Y, so we say that X has a better inhibitory activity than Y, even though the IC50 of X is actually larger.